Hello and welcome to m253. My name is Lapuz, and in this video we're gonna do checkpoint 5.48. In this checkpoint they want us to consider D, a region in the XYZ space defined by 1 less than or equal to x less than or equal to 2, 0 less than or equal to xy less than or equal to 2, and 0 less than or equal to z less than or equal to 1. They want us to evaluate this triple integral over d of x squared y plus 3xyz dv using this transformation. U is equal to x, v is equal to xy, and w is equal to 3z. Alright, so let's get this set up. And I think the first thing we want to do is we want to see how this transformation will actually work with the actual domain or the actual region that we're looking at. So let's take a look at it. Let's try to find the region in the UVW space that would coincide with this. Let's rewrite everything over. We have 1 less than or equal to x less than or equal to 2, 0 less than or equal to xy less than or equal to 2, and 0 less than or equal to z less than or equal to 1. So given this transformation, I can see that u is just equal to x, so that's a direct translation here, where instead of an x we're going to have a u, so u is going to go from 1 to 2. Now this whole thing here can be seen as v, so that's another nice transformation for us. V is going to go from 0 to 2. And then now we have z here. If I want to figure out what w is, w or z is equal to w over 3. And so if I write w over 3 between 0 and 1, then w, if I multiply all three sides by 3, I'm going to get 0 less than or equal to w less than or equal to 3. So those are going to be my new sets of limits. Alright, next thing we want to do is we want to figure out our actual transformation. What we are given here is our UVW transformation. So this is like our T transformation, UVW, and that gives us our X, which is U, our Y. Well, we don't know that. And then our Z is another thing that we don't know. So we need to figure out what this transformation is, what X is equal to, what Y is equal to, and what Z is equal to. Okay, so how we're going to do that? I think it's clear that X is equal to U. We already got that from our easy transformation. And then we have V is equal to XY. So if X is equal to U and Y is Y that we need to solve for, then that whole thing is equal to V, then Y is equal to V over U. And I think that's the V over U that we'll use here. And then the Z is equal to 1/3 W. I think we already had that figured out over here. And so those are going to be our functions. So U over V and 1/3 W. This is a U, excuse me, U over V. Okay, so basically these three functions will help us find our Jacobian. So to find our Jacobian, we need the x, y, z functions as functions of u, v, w. And this will give us a 3x3 matrix of derivatives. And in the top row will be the derivative of x with respect to u, with respect to v, and then with respect to w. The second row will be the y function with respect to u, with respect to v, with respect to w, and then our z function with respect to u, with respect to v, and with respect to w. Okay, what are those? The derivative of x with respect to u is 1, and there's no other variables there, so those are going to be 0. The derivative of y with respect to u, the derivative of 1 over u is negative 1 over u squared, and then we have a constant v with respect to u. The derivative with respect to v is just 1 over u, as if u was a constant, and then there's no w's in this last one. And similarly, we're going to get 0, 0, 1/3 for the derivative of z with respect to u, v, and w. Now this is a lower triangular matrix, and whenever we have a lower or upper triangular matrix, the determinant is just going to be the product of the diagonals. So our Jacobian is just 1 over 3u. Okay, that seems like it's working out pretty well so far. And I think we are ready. We have the limits. We have the Jacobian, and now we just have to transform the integrand in terms of x, y, and z. So our integrand will be integrating over a new solid with u, v, and w. And now let's see what happens in here. We have x squared y, so our transformation here is u. X squared is going to be u squared, and y is going to be v over u. And then plus 3 xy. Now xy is v, right? We had that transformation. Xy is equal to v, so that's just going to be v. And then z, what's z equal to? Z is equal to 1/3 w. So that's my whole integrand. And in the dv now will transform into the Jacobian, which is just 1 over 3u. And then now we have du, dv, dw. And it doesn't look like it matters which order we do this in, because they're all constants, which is great. So I'm just going to write dw, dv, du, and we'll see where it goes from there. All right, let's simplify a few things. When we simplify a few things, I'm going to get this to just be uv. All right, because one of the u's goes away, and here the 3's are gone, and this is just a vw. Okay. Oh, but we're also adding this 1/3, 1 over 3u. So we have a 1/3 that can go out. The u's here would cancel. So we got a 1/3 that can go out. The u would cancel with this u, so that's just the v for the first term. And then nothing cancels, unfortunately, so we have vw over u for the second term. All right, now let's set up the integral that we're actually going to solve for with the limits and all. So our integrand is going to be 1/3. Let's take that out. We have a v plus vw over u, and the dw, w goes from 0 to 3. The dv, v goes from 0 to 2, and then the du goes from 1 to 2. All right, let's do this piece by piece. The innermost integral with respect to w. So this is going to be vw plus, now this is w squared over 2, so it's vw squared over 2u, and we're going to evaluate w from 0 to 3. And with 0 there, that goes away, so it's just going to be 3v plus, and then this is 9, so that's 9 halves v over u, and that is the integral. We got a minus 0 there, so that's the integral of the innermost integral, and then now we bring it down to integrate from 0 to 2 of this new integrand. It's 3v plus 9 halves v over u. This time we're integrating with respect to v. And what is this going to equal to? With respect to v, this is going to be 3v squared over 2, so it's 3 halves v squared minus another squared, so that's 9/4 v squared over u, and we're evaluating this v going from 0 to 2. So again, zeros go away. We put 2 in here, we're going to get 4, cancel with a 2, so that's just going to be 3 times 2 is 6, minus, and then putting another 4, so that's going to be 9 times 1 over u, and then 0 for the second part of your FTOC. And then now we get to the 1/3 integral from 1 to 2 of 6 minus 9 times 1 over u du. So that is going to be a 1/3 of 6u minus 9. This is ln of u, going from 1 to 2. Okay, so we will get a 1/3, and then this is going to be a 12 minus 9 ln 2, and then minus 6 minus 9 ln of 1, but ln of 1 is equal to 0, so that's going to go away. And then we have a, we have a 1/3. We had a 12 minus 6, that's going to be a 6 minus 9 ln 2, so this is going to be a 2 minus 3 ln 2. Alright, so that is our integral. We did it by hand, and good. We did the transformation. So what did we do? Just to recap, we have the transformation given to us as a u as a function of x, y, and z, uv. So this is essentially the pullback, the t inverse. We need to figure out what x, y, and z are equal to. So we did that by some substitutions, and then we figure out, based on our solid, what the new limits are going to be. I guess we did that first. So we made our new limits with a uvw instead of an xyz. We found the transformation t. We took that transformation t and we put it through the Jacobian 3x3 matrix, happened to be an upper or lower triangular, so that the determinant is just the product of the diagonals. We rewrote our integrals, so we changed all the variables from xyz to uvw. We included the Jacobian, and then we integrated with respect to wvu in that order. And because these are constants, we could have done it in any order we want, but we just happen to have done it this way. We integrated from inside out, and we got a result. All right, hope that helps. Good luck.